Hello and welcome. My name is Brandon Morgan, and in this video, I'm going to be giving an explanation to the code I gave on my Medium article for benchmark test function 1. So if you have no idea what I'm talking about, I am in the works of making an article that will eventually be posted before this video is posted, in continuation of my full course on evolutionary computation. And in this course, I'm continuing to simply explain evolutionary computation and genetic algorithms as a whole. And in this video, I'm going to be giving an explanation to the code I gave over the benchmark test function, function 1. So what exactly is the problem statement? Well, the problem statement is the following. We are given the following 6-hump camelback function. It is a trivial optimization problem that we want to minimize. And it is usually in two different forms. Now these are the same function, it's just that the bounds are different. We are going to be doing the optimization problem on this function here with these bounds from x1 is between -2 and 2, and x2 is between -1 and 1. And you can see the equation of the function here. So our job is to find the global minimum of this optimization problem. Now for details about the algorithm design, we are going to have these standard arguments like normal. We're going to have probabilities of crossover and mutation, the initial population size, the mutation bound percentage and percentage of elitism, along with the maximum number of iterations. So these are the standard arguments we used in our previous video. However, in this video, we are going to include some new arguments. Previously, we only did selection through roulette wheel. However, now we are going to do it with a range of values. A range of methods. We're going to have an option for roulette wheel selection, random selection, and tournament style selection. And in addition to that, we're also going to have a way for the user to denote the reproduction method. Previously, we've been just using crossover as the average method. However, we're also going to now include a value. That way we can use the intuitive crossover method. This is terrible. All right, and here we are back in my PyCharm. Now, before I implement all this from scratch, I'm going to first give a little bit of a debug so that I can walk through all the steps of the algorithm. So now I'm just going to run this. We're going to run our evolution algorithm with a 75% chance of crossover and mutation with the given bounds. So here we have our upper bound for our x1 and x2 variable. Here we have the lower bound for our x1 and x2 variable. We're going to have the reproduction and selection method set at 2, meaning we're going to use tournament style selection with a 20% of the population size for the tournament size. And reproduction method 2 is the intuitive crossover method. And we're going to mutate each bound by 1% of its total range. And we're going to have an elitism of 20% as well. So let's just run right through this. So here we have our initial generation, our initial 10 randomly, uniformly generated individuals. Here's their x1 and their x2 value. So now let's get the upper bound, the lower bound, and then we're going to take the absolute values of these and add them together to get the total range. And then we're going to multiply this by the mutate bound percentage, which is 1%. This will give us 1% of the total range of each variable domain. And this is going to be the maximum value that we're going to mutate by. So now let's get our tournament size. So right now our tournament size is 20%. So this simply just calculates your 20% of your total number of individuals, which would be 2 for us. Yep. Now we're going to calculate our elitism coefficient, which is simply the starting point for our index. I'll explain that when I implement this from scratch. So now we're just going to loop over our algorithm a total of max iter times. First things first, we're going to calculate the fitness of our individuals. And we're going to do some diagnostics right here. So we're going to calculate the max and the mean values, all good stuff. And then we're going to print that information out. So here we have our best fitness and then our mean fitness. So since we're not finding the maximum, we're going, let me back up a little bit. We're first going to scale our fitness simply because, as we can see, our fitness contains negative values. So we're going to scale it to make it always positive. So now all the fitness values are positive. Since we're not finding the max, we're finding the min, we need to scale our fitness again such that smaller values are larger and larger values are smaller. So we can see here the max value is 3.3 and the min value is 0. Once we scale this again, the max value is now 1, which occurred at the 0 index, and the min value is now 0.23, which occurred at the large index. So now what we're going to do is we're going to create our fitness again. So because we're not using proportional roulette wheel selection, we don't need to scale our fitness. We're simply just going to set it equal to our scaled fitness. And then what we're going to do is we're going to column stack our fitness with our indices. So what is the purpose of doing this? Well, here's the problem. If we have elitism, if we're performing elitism, we need to choose the best 20% or whatever percentage of our initial generation, of our current generation, and then continue that on to the next. So how do we do that? Well, we need the fitness values. That way we can determine who's the best 20%. So here we have the fitness values. But the problem is we need to sort these fitness values. But once you sort them, how do you know which fitness value goes to which individual? Well, what you can do here is you can add an index. So for example, 0 index corresponds to the first individual, second individual, third, fourth, fifth, all the way up to the 10th individual. So now we sort this temp matrix based upon the fitness value. So if I was to show this again, now here we have our sorted fitness values from least to largest, and here are the corresponding sorted indices. So now we can use these indices to backtrack into our original individuals. So because we are using elitism, we're going to set our best index equal to elitism. We're going to create a range of values, which would be a range from 8 to 10. So because we're doing 20%, we want the best 2. So it would be a range from index 8 to 10, which would be these two. So our best indices would be 2 and 6, as we can see here. Next, since we are doing tournament style selection, we're going to perform that. So what we do here is we loop over a total of n times, where n is simply the number of individuals, which would be 10. And first we create a random tournament. So simply our tournament size is 2. So we sample from our total range of indices, which would be 5 and 7. And now what we do is we need to find the best individual. Well, we do that by simply using these indices as, we use these indices to index our fitness and then choose the max fitness value. So if we were to say fit, here are our fitness values. Then we get the fitness values at our indices, which are these two. We get the best index would be 0, so this value here. So our competitors at index 0 is index 5. So index 5 is the selected individual. And we simply repeat this a total of 10 times. So now, once we have our first set of parents, we calculate our second set of parents by simply just randomly choosing from our first selected. So these are the indices for the first selected, indices for the second selected, and now it's time for reproduction. So simply what this does is we have our indices for our selection and our mates, and we simply just use these indices to index our current generation, as we can see. So we pull out the generation individual along with our fitness value. So I'm going to step into this. So here is our first parent, and then our second parent, the first parent fitness value, and then the second parent fitness value. So now we're going to calculate our random values. So because this value is less than our probability of crossover, which is 75%, we are not going to cross over. So what we do here is we calculate the fitness values. So F1 is bigger than F2, therefore parent 1 would be the default, as we can see. And now we're going to mutate that child simply because our P sub 1 is less than our probability of mutation. And now our constant that we're going to mutate by, so we're going to mutate the x1 by this maximum value, and then mutate our x2 variable by this maximum value. And that's exactly what we do. So we loop over j, which j corresponds to the index of our variable value. So the constant mutate at index j is 0.04, which is the 0. Our child is this. So after we mutate, let's see what it looks like. After mutation, we can definitely see here that we mutated the x1 by about 0.04 and the x2 by about 0.001. So now that would be an example of reproduction. However, I'm going to loop until we've reached the crossover, simply because I want to show you guys what that does. So since we're using the second method of crossover, we're going to do intuitive crossover. So I'm going to step into this method. So here is our first parent, and here's our second parent. So we create our child as a copy of the first, and then what we do is we simply switch the variable values. So we'd make our offspring equal to this variable value and this, or it'll be this variable and this variable value. So I'm just going to run this through. So here's our child. So our child inherited this allele from the second parent, and then the second variable value from the first parent. So this would be an example of intuitive crossover. So instead of averaging these variable values together to create some type of hybrid, instead you just switch the variable values. So now that we've done that, let's just continue on until we exit. So now we have our next generation, as we can see. Now what we need to do is check for our bounds to see if any value is larger or greater than our bounds, but just for save time, I'm going to skip past that. And now let's see what our generation should look like. However, it doesn't look like any of them went past the bounds whatsoever. So now we're going to essentially take the worst 20% of our next generation and replace it with the best 20% from our previous generation. So to do that, we need the fitness value of our current generation, and then we need to sort these again. So we're going to sort this from 0 to 9. Here's our indices, and then our unsorted fitness values. Now, if we're finding the max, we'd essentially want the smallest values down here at the bottom, which would be the worst. However, if we're finding the min, we want the largest values down at the bottom. So that's why there's a difference here. So we sort them, call this function again. So now we have the best values up top and the worst values at the bottom. And then here we calculate the indices to replace, which would essentially be, so best index to n. S would be, oh, did not give it. So it starts at index 8 and it goes to index 10. So if we were to call this right here, what exactly does it do? It returns indices 0 and 9, as we can see here. These would be the indices, the unsorted indices of the worst individuals. However, it converts it to a float, so we need to convert this to an array of type int, and then convert that to a list. That way we can use it. So here's our indices to replace 0 and 9. And essentially what we say is we're going to say gen next at these indices, replace with the previous generation at the best indices. And once we do that, so we can definitely see here at index 9 changed with this. So this individual changed with this one, and then this individual changed with this one. So now that is simply our next generation. And essentially we just keep on looping over this maximum total of times. I'm just going to run it through. So that ran all the way through. We found the global minimum, which occurs at negative 1.03616. Excuse me, negative 1.0316. So now what I'm going to do is I'm going to clear all this up and then code it from scratch for you guys. All right, now I'm in PyCharm, and we're going to start implementing this function from scratch. So first things first is I'm going to import our libraries, simply NumPy and matplotlib, which is we're going to be using to plot out the successive generations of our algorithm. So first off is we're going to define some functions. In the previous video, we stuffed all the main components of our algorithm into a single function. Now, because we're adding more complex components, I need to flesh it out. So instead of just sticking it all inside of one function, I'm going to break it out into multiple functions. So first off, I'm going to create our scale function. This function is going to be used when we're using roulette wheel selection. So simply because roulette wheel selection, it requires all the fitness values to be positive. We're simply going to add the absolute value of the minimum to each fitness value so that they're all positive. And next, if we're going to be finding the minimum, we need a way to scale this such that the smaller values are larger and the larger values are smaller. This is done by the following formula. If you read my article, you should know exactly what I'm talking about. If not, please go do your homework. And then now I'm going to define our roulette wheel selection method. We're going to take in a cumulative sum and n, which is the number of individuals or how many times we should perform this algorithm. So we're going to say our indices as a list, and we're going to make a random array of uniform values between 0 and 1. And we'll say for I in the range from 0 to 1, excuse me, 0 to n. We're going to preset our index to 0. We're going to say while cumulative sum at this index is less than r, then we keep on increasing the index. And then once this value here is larger than our random value, that's the index that has been chosen. As stated before, if this is some type of alien language to you, please go back and read the article. Next, we're going to define random selection. Now, random selection is extremely easy. We just simply return a list of random indices from the entire range, and we're going to do it with replacement. That way, multiple values can be chosen. That way single values can be chosen multiple times. Now it's time for tournament selection. We're going to pass in our fitness values, our tournament size, and then n, which is the number of individuals we should create. We're going to say selection. So we're going to say for I in range from 0 to n. We're going to get our competitors, random dot choice from the range of 0 to n of tournament size. Replace is equal to false. We don't want multiple competitors being the same. And then we're going to say the best index is the index such that it has the maximum fitness value. So competitors is simply going to be a range of values between 0 and n, which are our indices. We'll use these indices to look up the fitness values of the corresponding individuals. We find the index of the max, which is exactly what argmax does. It returns the index of the max. And then we simply append that index. So now we have the index of the max from competitors. So to retrieve the actual index, we need to index competitors at that relative max. And then append that to selection, and then return selection. So now we've simply gone over all the selection methods and the scaling methods. It's time to move on to the crossover methods. So previously, our crossover methods were only designed for one variable, but now we need to accommodate multiple variables. So in this crossover method 1, and this is going to be the average technique, where we take the average of both parents. So what exactly is const cross? Well, const cross is the same as the gamma value that we used previously. So we're going to say our child is equal to a copy of P1. And we're going to say for j in range. And we're going to loop over every single variable value in our parent. So if this had 2 variable values, then, why is that? Okay. So if this had 2 variable values, then it will loop over twice. If it had multiple variable values, it would loop over multiple times. And it's equal to 1 minus const cross times P1 plus const cross times P2. If const cross is kind of crossing you up, just replace it with a different variable name such as gamma. That might be more useful. So now simply what we do is as stated before, we loop over all the variable values, and then simply we just take the average of those parent variable values. Now the second one is going to be the intuitive crossover technique. Now remember, what this one does is it takes, instead of averaging the variable values, it switches them, meaning it has a probability of inheriting a variable value from parent 1 or parent 2. So we're going to make our child a copy. We're going to define n to be the shape, which is simply the number of variables. And we're going to create a list of random numbers, which is going to be a list of random numbers, or excuse me, random ints between 0 and 1. And there's going to be exactly n of them, n being the number of variables. We're going to say if random nums is at 0 is equal to 0, then the child at 0 is equal to p2. If random nums at 0 is equal to 1, then child at 0 is equal to p1. So this is exactly what we're going to do. We're just going to see if it's 0, inherit from parent 2. If it's 1, inherit from parent 1. Now the problem is this. You might be thinking, well, this is not beneficial at all. Why is it hard-coded? We can use a loop. That's exactly what I'm going to do. But the problem is this. If there's 2 dimensions, meaning there's only 2 variables, then you have a 50% chance of inheriting both genes from the same parent. We don't want that. So we're going to hard-code the first 2. So if n equals 2, meaning there's only 2 variables, then we're simply just going to hard code this. That way we have an even split. We're going to hard code. So if random nums at 0 is equal to 0, then what we're going to do is we're going to switch it up. Parent 1 and parent 2. This way we have an even split of the parents for crossover. Else, meaning the number of dimensions is larger. We're going to say for j in range. This is where we're going to create an actual loop for j. And there we go. And that should be it. Well, now we're just going to return our child. So the next thing we're going to do is mutation. Now mutation is extremely simple and easy. Mutation method 1, we're going to have a child and a const mutate. Const mutate is the value that we want to mutate by. Now the thing is this. Since we're dealing with multiple variables and each variable might have a different domain size, the value, the maximum value we might mutate by is going to be different for each variable. So const mutate to that is actually going to be a list of maximum values. So we're going to say our random nums actually we don't really need that. We can say child at j, the jth variable value is going to be equal to np random dot uniform from the negative max value at that particular variable value. We're only going to do it once, and we're going to extract the first value. And that's it. That was really simple. Next thing we're going to do is define the reproduction method. So this reproduction method is going to take in the parents, their fitness values, the probability of crossing over, the probability of mutating, the maximum values to mutate by for the bounds, and then the reproduction method. And it's simply going to create the offspring for this pair of parents. So first things first is we're going to get our random values to see if we cross over or not. So we're going to say if the random value at the first index is greater than, excuse me, less than the probability of crossing over, then we cross over. So we're going to say if, now since we're crossing over, we want to know whether or not we're going to use the first or second crossover method. So if we're going to say the reproduction method is equal to 1, then now we're going to create our gamma value. Our gamma value is going to be some type of random normal value. Previously we did a uniform between 0 and 1. However, this time we're going to use a random value centered at 0 with a standard deviation of 0.15. And we're only going to use 1. And then now the child is going to be the crossover method of 1, which is the average technique, and then the gamma. If reproduction method is equal to 2, meaning we're going to use the intuitive crossover method, we just need to pass in the parents. Now, if we don't cross over, we need the offspring to be the fittest from the parents. So we're going to say if f1 is less than f2, that means parent 2 is the better. So we're going to copy from parent 2, else child is equal to np copy of parent 1. Now that we've crossed over, it's time to mutate. So now we created 2 random values here. So we already used the first index. Now we're going to use the second index. So if now the second random value is less than the probability of mutating, then we mutate. Now we don't need to return assign anything, because this works by reference of object, meaning we actually change the object itself when we pass it through. So we're going to say child, and then const mutate. And then we're going to return the child. So we pass in child, it actually changes it by reference, and then we just need to return it. So now we've done essentially almost all the hard work, all the functions and all the components we needed. So next thing is to implement this algorithm in our evolve function. So we're going to say definition def evolve, define our initial generation, probability of crossover, probability of mutation, our bounds of the problem, our fitness function, our mutate bound, which is simply the percentage of the bound that we want to mutate by, our tournament size, our tournament elitism, and we're going to preset these to 10%. And then our maximum number of iterations, which we're going to preset at 100. Info is equal to true. Simply, this is going to be a variable whether or not we want to print out information at each iteration. And then find max. So we're going to give our algorithm the ability to choose whether or not it finds the maximum or the minimum. So we're going to say find max is equal to false, meaning that it's always going to find the minimum. So first things first is we're going to create our generation from our initgen. It's going to be a copy. We copy it simply because if we don't and we just assign it, if we change gen, it's actually going to change initgen. We don't want that. So at each iteration of the algorithm, we're going to store the best fitness values and the mean fitness values. So we're going to create a list, and at the end of each iteration, we're going to append the best to these lists, and we're going to plot them out. So now what we need to do is extract the bounds. So the upper bound is going to be equal to the first index of bound. Now remember, bounds is going to contain 2 lists. The first list is the upper bound and the second list is the lower bound. So in our example, x1 is between -2 and 2, and x2 is between -1 and 1. So bounds is equal to 1, -2, -1. So we have the upper bound of our variable values and then the lower bound of our variable values. So we need to extract the upper bound, which would be the first index of our grand list. And then now we're going to do the same for the lower bounds. And now what we're going to do is create our maximum value to mutate by. So we're going to say bound mute is equal to mutate bound, which is the percentage, and we're simply going to times this percentage by the absolute value of the lower bound plus the absolute value of the upper bound. So what this does is the following. So in our example, if we were to add this plus this, the absolute value, we would eventually end up with 4, and we'd end up with 2 for the second variable. And then we take this array, and then we multiply it by our mutate bound, which in our case would be 1%. And this would give us 0.4, I think, and 0.02. So now these are the maximum values that we're going to mutate by. So in our example, that's exactly what this value is going to be. It's going to be a list of these values. So That's why up here in our mutation, we index through our mutation bound, because there's going to be multiple for each, there's going to be one for each variable. So now we're going to get the shape of our generation. That way we have a track of how many variables and how many individuals there are. Then also we're going to set up our tournament size. Now the problem is this. Let me write it out and then I'll show you exactly what I mean. So tournament size right now is a percentage. We want an actual value. So we're going to convert this to an actual value. We're going to say integer is equal to n times tournament size. So if n is 100 and tournament size is 10%, then that means it's 10. But let's say for some reason tournament size was 10%, except our initial generation size was only 3. Well, 10% of 3 is 0.3. You can't take 0.3 as a tournament size. So we include a maximum, meaning it's going to choose the maximum between 1 and this value. That way, if this value falls below 1, it simply just chooses 1 as the maximum tournament size. So now we're going to say if elitism is equal to 0.0, meaning that we are not using elitism. We're simply going to say elitism is equal to -1. And we're going to do the same thing as we did previously for tournament size. We're going to say else elitism. We're going to convert this this percentage to an actual number. So we're going to convert this by saying the following. We're going to say n times elitism, which is going to give us the percentage of our population to always carry over. We're going to round that to the ceiling, and then we're going to say subtract. So let's say if elitism was 10% and n was 100, this would be 10, and then so the ceiling of 10 would be 10, and then 100 minus 10 would be 90. So this would be the starting index that we index by. And I'm going to explain that a little bit in a minute. So in this video, I'm going over a lot of the concepts I covered in my previous video on the short trivial example. So if any of these things seem a little weird, please check out that video, as it'll explain everything. Almost everything. So now what we're going to do is the following. We're going to we're going to loop over our algorithm a total of max iter times. And at the very beginning of each iteration, we're going to calculate our fitness value. And then here we're just going to do some output messages. So we're going to say if we're finding the max. So we calculated the fitness. We're going to calculate the mean of our generation. If we're finding the max, that means the fit best is the maximum from the fitness value. And then the best index, which is the best individual, is from the argmax. Now for finding the minimum, that means the fit best is actually going to be equal to the minimum of the fitness. And the best index is going to be equal to the argmin of the fitness. And now we're just going to append these values to our lists. We're going to append generation at best index. Best fitness dot append best fitness. Oh, that's wrong. Dot append fit best, and then mean fitness dot append mean fitness. And now we're going to say if info, meaning we're printing out things. I'm just going to copy and paste this from the thing I'm copying from. We're going to print out the following message. Generation. We're going to print out each generation, denoted by K, with the best fitness and then the mean fitness. So now that we've done that, it's time to start our algorithm. We're going to use the same components in the previous video. First, we're going to scale the fitness. So we're going to scale it using the first one to make sure it's always positive. And if we're not finding the maximum value, that means we're finding the minimum value. And so we need to scale the fitness again. That way, smaller values are larger, and now the larger values are smaller. So now we're going to create our indices. We're going to say if selection method is equal to 1. That means we're doing tournament style selection. So we're going to create our proportional distribution. So we're going to say our fitness now is equal to our scaled fit divided by the sum of the scaled fit. However, if we're not doing proportional selection, then we don't need to scale our fitness whatsoever. We're just going to set it equal to our scaled fit. So now what we need to do is the following. We're going to create our temp matrix dot column stack. We're going to stack our fitness and our indices. MP-arg sort. Now we're going to sort our temp matrix based on the first column. We're going to sort all the fitness values, and we're going to say if elitism is equal to -1. Now, elitism only equals -1 if the percentage was equal to 0. That means that we're not doing elitism. However, we're going to say if not equal to 1, that means we are doing elitism. Our best index is equal to elitism, simply because, as I stated before, if n was 100, elitism was 10%. 10% of 100 is 90, is 10. And then we do 100 minus 10 is 90. So we're going to start at the index 90 and iterate until 100. These would be the best 10% of the generation. So our best indices would be a range from our best index to n. And now we're simply going to convert this to an array. So remember, our temp value contains these sorted indices. So we take our best 10%, and then we index on these best 10%, and then we get their original unsorted indices. And these would be the original indices for the corresponding individuals. So if selection method is equal to 1, that means we're using proportional selection. We're going to create our cumulative sum of the fitness values, and then our selection indices is equal to roulette wheel selection of our cumulative sum, and we're going to do it n number of times. Else, if our selection method is random, then our selection, 2 is actually going to be tournament style selection, not random. We're going to pass in our fitness, our tournament size, and n. And then finally, if selection method is equal to 3, our selection is equal to random selection. And then our mates are simply going to be random values chosen from our selected indices without replacement. So now that we've done that, it is time to create our offspring. Now remember, this reproduction method up here only takes in 2 parents at a time. So we're going to have to loop over this a total of n number of times to create an offspring. So we're going to create an array or a list called children. Say for I in range from 0 to n. Children.append reproduction. Now this is going to be some tricky indexing. We need to get the parents. Now selection only contains the indices, so we need to index from selection. So selection at I returns an index, and we're going to use that index to index the actual individual. And we're going to do the same for the mate. And now that we have the mates, we need their fitness values, which would be the same fit at selection at I, and then fit at mates at I. And then we're simply going to pass in the probability of crossover, probability of mutation, the bound to mutate by, or the maximum value to mutate by, and then the reproduction method. So there we have that. Now it is time to create our next generation. It is going to be an array of the children. We're going to convert this to as an array. There we go. Now, after we've done this, once we mutate, we might actually mutate some of the values such that their variable values are outside the bounds. So we need a way to check on the bounds. So if bounds is not none, meaning that there are no bounds, assuming there are bounds, we're going to loop for each individual in our next generation. And for each of these, for each individual, we're going to loop over every single variable value. And I'm just going to copy and paste this because I don't feel like typing it out. Simply, we're going to say if the current individual from our next generation at variable j is bigger than the upper bound, then we set it equal to the upper bound. If it's lower, then we set it equal to the lower bound. This way, none of the variable values are outside the bounds. Now we're going to say if our elitism is not equal to -1. So we've created our children, and now we need to replace the worst with the best from the previous generation, only if elitism does not equal -1, which, if you remember, that only occurs if the elitism percentage was equal to 0. So now we need to calculate our next fitness of our next generation. And then we're going to sort based on this fitness value and replace the worst with the best. So like normal, we're going to create our temp matrix, column stack, and the next fit with the indices. We're going to say if find max, temp.arg sort. Now, why am I making an if statement? Well, the reason why is the following. If we're finding the maximum, that means we want to replace the smaller values, which is what we're doing here. This negative sign simply makes it such that the values at the very top are larger and it's decreasing. Now, if we want to find the minimum, that means we want to replace the maximum. So we do the opposite. We sort it in ascending order. That's what this one does. So now what we do is we calculate our indices to replace. And we have to convert this to an array. Let me just type it out first. So it's going to be temp best index, which would be 90 in our example, assuming we have 100 individuals, and an elitism constant of 10%. So if you remember, this temp matrix holds the fitness values along with their indices. We sort the fitness, and then as a result, the indices are now in sorted order. So we have to get the the worst 10% of those indices. So these would be the indices that we want to replace, but we have to convert this to an array of type integer. That way we can actually use them as indices. And then we're going to convert it to a list. So our next generation at the indices to replace is equal to our gen at the best indices. Now, best indices are the indices from the previous generation that were the best. So now we've created our next generation. It's time to set it for the next iteration. So the next iteration uses gen. So essentially what we do here is we say gen is equal to gen.next. And this presets the next generation for the next iteration. And that is actually the entire algorithm in its entirety. The only thing left to do is simply just plot out certain values. So at the very end, we want to do some diagnostics. So we're going to create a range of values from 0 to max iter. We're going to plot the mean fitness, and the best fitness, and then we're also going to plot out some values to determine whether we're going to plot out S, R, E, and T, where S represents the selection method, R represents the reproduction method, E represents the elitism, and then T represents the tournament size. So now it's time to test our algorithm. I'm just going to copy and paste the 6-sump camelback function. So there it is. You can pause and look at that more in detail. And the next thing I'm going to do is create our initial generation. It's going to be of size 10. That's going to have two variables. So the first column is equal to the first variable, random.uniform between 0 and 2 of size. Do the same thing for the second variable. Now we have that. We're going to create our bounds. Now that we have that, we are going to call our function. So our best individuals, now this is simply the last generation. So we're going to return, excuse me, not the last generation. This is going to be the best individuals over the entire course. Is equal to evolve initGen is equal to our initial generation. Probability of crossover, let's say, is 0.75. Probability of mutation is 0.75. Our bounds are equal to bounds. The fitness function is going to be a pointer to the 6-up camelback function. What else? Our reproduction method is going to be the second one. Why is it giving me that an error? Let's see. Did I not define this? Okay. So it appears I actually forgot these. This is going to be reproduction method is going to be equal to 1. And then selection method is also going to be equal to 1 as a default. Reproduction method is going to be equal to 2, which is going to be the intuitive crossover technique. And then our selection method, let's go with tournament style selection with a tournament size of 20%. Or yeah, let's do 20%. An elitism of 10%, maximum iterations of 100. Info is equal to true, that way we want to print it out. And we want to not find the max. So now let's test this out and see how it works. Modular bias no empty. There we go. Mutate bound is missing one argument. Okay. Mutate bound is going to be equal to 1%. Okay, so there we have it. So it started out at a best fitness of negative 0.92 with a mean fitness of 1.09, and it converged to about negative 1.0316. Now this is exactly where the minimum occurs at. So I'm just going to print out the best individuals, stop and rerun. Let's see. It appears it stopped. Hold on, give me a second. All right, I figured out what exactly was happening. It somehow entered some type of infinite loop when it was plotting. This simply occurred because when I appended here the mean fitness, I appended the mean fitness list itself instead of actually the fit mean. So now let's, if we can cooperate, you can do it, and I believe in you. There we go. So let's run it again. So it runs. Here we have our output. So we can definitely see the mean fitness started up pretty high, and it slowly converged, probably at 25, 30 generations. Now, let's see what we can do with some different parameters. Let's say our initial size is 100. Probability of crossover is 25%. 25%. Let's say we're going to use the average technique with random selection, elitism of 10%, and mutate bound of 1% still. So that still worked. So as we can definitely see, this was a very easy problem, simply because no matter what the input we give our algorithm, it's probably going to find the global minimum. Usually in most cases, finding the global minimum is dependent upon the hyperparameters of your GA. And so that's a major downfall of genetic algorithms as a whole. Depending on what you input as your initial parameters, it will definitely influence your final output. In fact, it is common to abstract and create a very simple GA or genetic algorithm, and then apply that to evolve the hyperparameters of a more complex algorithm on a function. But in this case, since the problem was so trivial, it won't be necessary whatsoever. So hopefully you guys have learned about genetic algorithms. Hopefully you guys, hopefully this video has helped you understand any questions you had over the code or how it worked. You can definitely tamper with this and even change the fitness function to be any function you want it to be. You could start adding your own benchmark test functions to this and test it. But in the next post and next video, we're going to be covering how to implement more advanced techniques for harder benchmark test functions. So stay tuned.